recording. So back to the King Seng will continue this paper on Quiver Floer homology group actions. Okay.
Okay, hi everyone. So today I want to talk about the topological setup in this paper, and then hopefully this will help us to understand the symplectic setup. Yeah, and we will see if we have time, we will see how we set up in the Lagrangian story. If not, then we will go to the next time. So today we will focus on graded intersection number between curves. So first of all, we will define what is curve in a surface. So suppose we have a surface S, uh, so a surface S. We want it to be oriented and compact. So what kind of surface you can think of? In this paper, two most important surface you need to think of is one is this, punctured this. And second you can think of is like some sort of Riemann surface. Okay. So we can also build a Riemann surface from this. You can get some Riemann surface out of it. But I don't want to discuss how to get until we reach a point we need to use it. Okay. So a set. So I denote. Denote delta as a set of mark point, finite mark point in my surface. So in this case, I have 4 points here. Okay. And then, what else? I should put it down here better. And then, okay, so next we want to discuss what is curve. So a curve in your surface is a subset of points such that it is either a simple closed curve. So closed curves mean it start or end at the same point. Simple mean it doesn't intersect itself. So let's draw a picture here. So simple is like you close yourself, okay, and then simple mean you don't want something like this one, okay, don't intersect itself. And these points should be in your interior, so it's in the S not. So you take out your boundary and your puncture and essential. So essential mean not contractible. Okay, let's draw some example. So you can, okay, maybe I give another condition first. So second is an image. So this is an OR. So either it's a simple closed curve or this is an embedding of a path. So embedding of a path, so the key point is the endpoint. So the endpoint can be puncture or the boundary of your surface, such that the inverse image of this is 0 and 1. Okay. So this transversal where is it? Transversality can be done by vectors, some vector field, I think. If it is not transverse, you can modify. But anyway, I will draw some example. So for example, you can take this kind of curve. Okay. You also can, maybe you can take this curve. Okay, one in the boundary, one in the punctured. You also can take this curve here. Okay, simple closed curve, but not contractible. So you can't take this kind of curve here, but because this is contractible. For Riemann surface, then this is like this kind of story. So you take a closed curve, but it's not contractible. So you take a closed curve, but not contractible. Okay. Okay. So you can see that these curves are smooth and unoriented. We don't impose any orientation, although the surface has. Any question? Okay, so before talk about the intersection number, we need to okay, before that, let me introduce a group. So there's a story in here, so we have to introduce a group of diffeomorphism. So this is a group. So you should see that diffeomorphism form a group. Okay, and there's some restriction in this diffeomorphism. So diffeomorphism is going from the surface to itself, such that if you restrict the diffeomorphism to the boundary is identity, and also you preserve preserve the puncture. So preserve the puncture doesn't mean you need to fix the puncture. You just need to maintain the set of puncture. So that means if you swap these two, both of them are still punctured, although they are swapped. Okay, so you are allowed to swap these two, or these two, or these two, or any two of them, three of them. Okay, as long as the set of puncture is the same. You can't say that you move your puncture to this place. So this is not. Okay, and you always fix this boundary of your surface. And this is quite important when we want to leave the diffeomorphism into covering spaces. Because you have something fixed, then that means the leaf can be unique. We will see later. Okay. Okay. Next, before we go into intersection number, you might wonder how you define it. Because, for example, let's say we draw this. So, okay, that's one function. So, for example, we have this kind of curve here, and then this kind of curve here. Wait, I want to draw like, let me see. So like this, and then maybe go up here and then intersect. Okay, so these are two perfectly good curves in your surface, but you can see that you can do some isotopy so that actually they intersect at only one point, right? So this one has 1, 2, 3, 4, but this one has 1. So to be technical, you need to introduce one notion called the minimal intersection. I won't discuss here because the definition is very technical. But the idea is you need to isotope so that you don't have this kind of bygone or something else.
Okay, so if that's something like a link, then the intersection, should that be one is up upon the other one? Since if you draw a picture like this, you don't know how these two curves intersect.
Actually it's just 2D, I think. It's just 2D.
Oh, okay.
Yeah. It's just 2D. It's not a 3D. Yeah.
Oh, I see. So there is only transverse or not non-transverse thing. Okay.
Yeah.
Yeah, I see.
Yeah. Right. Yeah. Right. Correct. So for this case, it's just 2D. So yes. Yeah. So minimal intersection is dealing with this kind of bygone. I don't want to go into the intersection, the definition, unless we will use it again. So after dealing with this minimal intersection, we can finally define intersection number. So given two curves, C0, C1, with okay, now this definition, I don't want to deal with curves that intersect at boundary of X. I just want them to intersect within S0, interior of your surface. So we define the geometric intersection number. Number to be lying in a half integer. So how we define it? So we define it to be 2 if C0 and C1 are simple closed curve and they are isotopic. And this long formula. So if otherwise, we will count their intersection at S0 to be 1, and then half the value if we count it at the puncture and a finite mark point. So not that I use a punctured or mark point interchangeably. So actually there's subtlety there, but it's the same in this case. If you view it as a mark point or you view it as a puncture. Puncture means you take it out. Mark point just means it's a special point inside. Okay. But yeah. But different way of viewing it will give different definition, but equivalent definition of diffeomorphism, group of diffeomorphism. If you take the right definition, they are equivalent.
Sorry, Keating, did I miss it? What's the C1 prime?
C1 prime. Okay, sorry. So C1 prime is like okay, yeah, you are asking the right question here. So C1 prime is something like this. So C1 prime is this minimal intersection. So you can pick some C1 prime representative. Okay. Not that in this case, you just need to isotope one of them. You can get this result, right? And of course, you need to show this is well defined. But I don't discuss here. It's in the paper as well. It's not very important. So not that you can just move this. Move this one out or move the other one in. You already get your desired result. So you only move the second one is enough. Okay, so let me note it down. So C1 prime is minimal intersection representative. Okay. So now given two curves in my surface, I can give you a geometric intersection number. But actually this is not good enough. Okay. I want more information. More information. Why do I need more information? For example, let me see. Okay, let me draw it out. I want more information. So, for example, this curve and this curve. Okay. So for I get, okay, let me draw another example here. Okay, so this tool should have a okay, I don't, maybe a bit confusing you. So let's do again. Let's do again. So let me redraw it. Let me redraw. Okay, let's, I think, start with an easy example. So why I'm saying this is not enough. Okay, let's say these two. This diagram. Maybe I do a then twist. Maybe I do sigma 2. Okay, what do I get? Or maybe I do sigma 3. Okay, I do sigma 3. What do I get? Sigma 3 is like twisting the third and fourth puncture anti-clockwise. So anti-clockwise is like this. Okay, so you elongate the second curve here. So become like this. Okay, maybe you can do another sigma 3. Okay, do another sigma 3. So what do you get? You get something like this. Agree? Okay. So let's say you do it again. Actually, I don't want to care about this line first. I just want to care about the blue line. What happened to the blue line? Okay. So I just apply to the blue one. I keep the green one. If you want, you can just throw away the green one. Just look at what happened to the blue one. Okay, if it confuses you. I just want to care. I just want to do something different to the blue one. Okay. And then what do I get? I get, okay, let's apply sigma 2 again. So what do I get? I get something like this. Okay. And then I apply sigma 3 again. And then maybe I draw it as a new curve here. So what do I get? So I get,
So sigma 2 is the map changing the second and third.
yes.
Okay.
Yes. Right. So yeah. So this is like a A3 acting on this D, maybe we'll call it D4 puncture. Okay. A3 acting on D4. Okay. So I do sigma what? Sigma 3. Yeah, sigma 3. Sigma 3, I get this, right? And then I do the last one. Last one is sigma 3 again. Correct? Correct? Everyone following? And then I get back to this. So I get back to the original curve, but you should see that I already go through some non-trivial action here, but I got back to the same curve. Correct? Right? But this bread is not a trivial, not identity. Okay, so if you use the intersection number, it doesn't really help because these two picture give the same intersection number. Okay, so we want something more rich, so we introduce bi-graded intersection number. Okay, hopefully this intersection number will distinguish these two intersections. Okay, yeah. And then this kind of so next, when we introduce bi-graded intersection number, we will hope that that will give a faithful representation. Okay, So so geometric intersection number is not enough. We want a bigraded intersection number. Okay. So okay, everyone following? So this two is the same curves, but different way of getting it. So we want these two give the different intersection number. Okay.
Is the first curve
Yep.
the same at the end as well?
This is the same. I keep the first the same. Keep the second the difference. Okay. I change the second. I change this, but yeah, but from the normal topology they are the same. But you can see that from this action is already is different.
I'm just looking like I'm just trying to think off the top of my head here, but so going down the left hand side of your page, and then you're switching the second and third mark points, so that the end point of that first green curve is going to be 3.
Oh, okay.
Three
that's
again,
fine. That's
and
fine.
then you got 3 to 4,
We
and then
we
let's go
don't.
back to.
Yeah, we don't distinguish the puncher.
Yeah, but
Yeah.
what am I trying?
Uh-huh.
I'm wondering whether the first one is it not this?
First one,
The last one is it not like?
Again. Can't see. Hey, wait. What are you drawing?
Yeah, I might be wrong here. I'm just like.
No. I'm this action I'm acting just on C. Okay, let's call this C and D, right? So I'm just acting on C. I just want to distinguish that. I just want to establish a result that such that these two are different things.
Oh, okay. So
this is not equal to C. I want this.
But
okay. Topology can't distinguish it.
Okay, but the green line and that final one's going to be different, yeah.
Green line should be the same, so it's the normal D. But this is this purple. This purple already. This purple is this. This is the purple.
You sure? Okay, maybe I'm just being me.
No, I'm not touching the green. I'm not touching the green. If you like, I can
go down the bottom of the page. Just
yeah.
So,
bottom. Yeah, bottom.
So if you do the sigma 2, so what happens to that green line?
Oh, I don't want to do anything to the green line. I want to keep the green line. Okay. If you are confused, I just start from. Right. I just start from this picture. If you are confused, I just start from this picture. I just want to do things on
C.
I don't want
you just want one of them. Okay.
Yeah, I just want one of them. Right. Yeah, right. Correct.
Okay. Cool.
Correct.
Thank you.
Yeah. Correct. Yeah. Okay. I don't want to confuse. Okay. You guys. Okay. So I just want to change the C. But topology, C is the same if you do this. But this is not a trivial break, right? This is not a trivial break. This is not the identity. Okay, so we want to distinguish these two using intersection number. Okay. Now we introduce a bigraded intersection number. So to introduce a bi-intersection number, we need to have some setup here. So why I introduce the geometric intersection number first? Because it will be based on that formula. So first of all, let PTD. So now we already shift to this. Okay, we already shift to this. Our surface is this. So what is this? This is the real projectivization of your tangent bundle. So what can you imagine is let's say I got a this. Okay, I got a this. And then I got my punctured this. And then every point I have a tangent space. Okay, I have a tangent space here. So it should be R2, right? Okay, it should be R2 because my this is just in C or in R2. And you projectivize it, meaning you just make it become an RP1. Okay, but in so in differential geometry language, you should take a trivialization, oriented trivialization. of my tangent bundle. And then we can get this P is actually RP1 cross minus punctured this. Okay, we projectivize it. And later we will see how useful is this projectivization. Okay. So now I think you can start thinking of a Lagrangian Grassmannian or something like that. You can start thinking of it. There's a parallel story to it. And now we want to know about the homology of P. Okay. So to know about the homology of P, for every point, for your every punctured point, you pick one circle. Okay, I call it lambda z. So winding positively. So positively, just put positively. So positively mean counterclockwise, right? So counterclockwise, lambda z. Okay. I think basic algebraic topology, you'll see that. So what's the basis of the first homology of this P here? So these two will form the basis of H1 P. Okay. So at every point you have one RP1, and then every RP1 you have one lambda z. Okay. So it's like a product. So this is like a product space, right? So you got this. Okay. Any question or not? Is it confusing? If not, then we continue. So we haven't quite get the covering right, covering space yet. Now we want to introduce a covering space of this. So this is the battlefield for us. So this is the place where we do the bigraded calculation. So this covering should be a Z cross Z covering. So Z cross Z with covering group Z cross Z. Okay. So actually, to tell you what group how I form this group, I need to tell you what cohomology class. Why? Because from the UCT, universal coefficient theorem. So universal coefficient theory use that this is isomorphic to form of H1 C cross Z. So I give you a cohomology class is equivalent to give you a homomorphism from first homology to Z cross Z, the group I want. So how do I define it? So I define it as if I take the lambda Z, I will send it to this point. If I take a point in RP1, then I will send it to this point. Okay. And then from here, we can already get the covering space. So we call it, we already call it P lambda. And then what else I need to tell you? I think I don't. Okay. So maybe, so there's an action. So yeah.
Sorry, is that homomorphism from H1P or H1C?
H1P. No C. Sorry.
Okay.
H1P. There's no C here. So yeah, C is a map, P is a space. Yep. Okay. Okay. So we did not kind equals z actually. So a bit of after I set up this space, I should be able to lift all the curve to the covering space, right? And also the map. So I will briefly explain here. So let F so suppose we have a diffeomorphism of this, okay, fixing the boundary and then permute the mark point or punctures. This actually induce a map from the projectivization of my tangent bundle. Okay, what happened to the tangent bundle? So I have a curve. I can take the tangent. Can you guys see or not? Okay, you can see. So at each point you have a tangent vector. So these are the point on your PT of your punctured disk. Okay. So if you move your diffeomorphism, of course your tangent space also move. So there's a tangent vector. I mean, sorry. So they induce a map from P to P. I called it P just now, right? And then I also introduce a Z cross Z covering space across P. So because of the fixing boundary property, I can lift to a unit lift. Okay, I don't go through the detailed argument here, but from basic algebraic topology, you should see this. Okay, using the lifting criterion, something like that. Because you already have a fixed lift on your boundary, then if you extend it, so it should be unique. Okay, and then the most important thing is we want to lift C, okay, because just now we want to introduce different of curves so that they have different intersection. So for C, we can only lift the part where the puncture is taken off. Okay, so you can lift. So let's take this section. So what happened is this XC, consider this SC. SC will take the point on the curve to X tangent space. And then this should have a lift. Is this clear or not? Okay, I think this map is continuous, so you can lift it up. Okay, so this lifting, so the lifting here, we will call it, so definition. I got a curve with this lifting is called bigraded curve. Okay. And then I will explain how useful is this thing. Okay. So next, we'll do some calculation. So I give some constructions first, and then I will do one example. So now we want to consider two different bigraded curve. We want to look at their intersection. And then so when we look at these two, we will look at the intersection. So either this intersection, so this let the Z to be in my this, but not on the boundary. Not that I don't discuss the case when they intersect in the boundary, but in the paper they have, but it's not very important. But this case is very important. So I want to consider a point Z where they intersect transversely, not on the boundary. So they can be punctured or in S0 in the interior. So in this case, you have two cases. For example, you can have C0, C0, C1. Okay, so this is in S0, or you can intersect at, okay, don't draw the circle first, later confuse you. So let's draw this. So this is C0, this is C1, or they intersect at a puncture. So C1, C0. So these are Z, these are Z. Okay, two cases. So how are we going to compute the bi-intersection number? Bi-graded intersection number. So first of all, let alpha be an embedded arc. Okay, I want clockwise. So clockwise arc from alpha minus C0 to 0, 1. Okay, that means this alpha is looking at something like here. Okay, here. Alpha. But you can note that I also can go from here to here. But actually, you can see that it doesn't matter in the calculation afterward. Okay. And then what else? So we need to lift to P, right? So now take pi to P with pi t is in P alpha t for every t from pi 0. So now we want to construct a path in P. This alpha is in just in this. So now we want to construct a path in P, which is the projectivization of my tangent bundle. So now you also can think of the Lagrangian story. Maybe you can imagine a bit.
Sorry, so
Yep.
what's the L there?
Yeah,
Alpha is
where is
from
the L?
0 to 1 to L?
What's the L? Why is the L here? Alpha to L. Let me. Oh, okay. Sorry. I forget to tell you one thing. So L actually is okay. Before taking this alpha, actually you can think of this alpha is part of a circle. So part of circle. So let me draw. So part of circle. So you can draw a circle around this intersection. You can draw a circle around this intersection. And then this circle will be called L. Yeah. So this L is not important, but if you want to check for well-definers of what, you will use the whole circle to check, because you can go in from this way up or this way down. But these two are related by this circle. This you can think of it as a homology. Okay, because if you surround this circle, you get the homology of this puncture. But I did define the where I gonna send this homology to, right, in this covering space. So it's important for the calculation. And not that in P, if you consider P, you need to compute how many RP1 you achieve by going around the circle. Okay, so these two paths is actually related related by this homology. Okay, so from here you can compute this, something like that. Okay. Okay, I haven't tell you how to lift alpha to the p, right? Okay, so I finished this first. So such that pi t is not equal to t alpha t. Okay, so what this pi doing is actually, okay, you consider this, and then you look at how to say, so p0 is t alpha c0, so it's something like, so infinitesimally close to it is like this. Okay, and then 2 pi 1 is 0. And then it says that such that, this is quite very important line here, such that pi t in the middle, you don't take this kind of line. Okay, what you can take is something like this. Okay, you can take 90 degree to the original tangent vector is fine. Okay, as long as it's not equal to that. So one example is you can take this kind of a curve. Yeah, right, curve in P. Okay. Okay, and then what else? Okay, so you see, not I still in P, right? So now I want to discuss P tilde. So I have to lift up this thing to P tilde. So I want to lift pi to my P tilde. So how do I lift it? So with so first I lift the starting point first. So I lift the starting point. So C naught alpha naught. Okay, I already parameterized it, so I call it alpha naught. And then the endpoint. So the endpoint should be this. Okay, and then there's a difference here. So there's a action of chi here. I will show you in a moment the example. Okay, so okay, I will show you example later. And from here, I want to define bi-graded intersection number. After I define this bi-graded intersection number, I will show you an example how to compute this thing. So you can compare this formula to the formula I gave you just now. So I introduced two parameters here. So it's Q1 and Q1 and Q2. Yeah. Okay, and then this. So the story of this topology is this bi-graded intersection number can give us the faithfulness of the break group action. Okay, and then the relation between this and the original one is, of course you have to show it, but I will tell you the property first. So if you set all your Q1 equals to Q2 equals to Q1, so you set all your Q1 and Q2 to 1, is actually 2 times the original geometric intersection number. Okay. Any question? If not, I want to go into the example of computing this local index. No question? Okay. So So how are we going to use this kind of local index to compute intersection number? So for example, we start with this. First, I need to tell you how to lift this the whole this into p tilde, right? The z cross z covering. Okay. So what I need to do is I just need to tell you how I lift these guys. And also maybe this one. Okay. So let's call it D1, D2, D3, and then B1, B0, B1, B2, B3. Actually, I just need to tell you how I lift this guy is enough to tell you how to lift the whole this into P tilde. You agree or not? These guys are like stratify. Can I say stratify? Like, you agree? Agree or not? If I lift this guy, I can lift the whole this to P tilde.
Is that because if you choose another point in the disk and then turn these paths into closed curves, then they are generators of some pi1 or
right. That's right. Okay. And remember, these curves are what we generate the Lagrangian submanifold thing. But these guys are just like indicator. Okay, these straight line are indicator. But these B1, B2, B3 are very important in our theory. Okay, so how are we going to lift this? So we lift this disk. So okay, so not that just now we consider the local index. For example, let me draw. So okay, so we need to know how to lift this, lift this, lift this, lift this, lift this. Okay, so you consider the intersection between DI and BI, or BI and BI plus. Okay, DI, BI, BI, BI plus. Okay, so when we lift them, we pick their local index to be 0. So that means I write it down in words. So pick dk tilde dk tilde such that mu1 z and mu2 z is equal to 0. Okay, this z of course depend on where you intersect, right? So I don't want to write it down. So depend on where you intersect, where you intersect, where you intersect, where you intersect, where you intersect. Okay. So okay, now do an example. For example, I want to look at this one. Maybe just 3 punches is enough. 1, 2, 3. And then I got my D1, D2. I got my sorry. I got my B here, B here. Let's say we want to look at this curve here. So let me draw it. I want to see this curve. Okay, I want to check this curve. Call it C. Okay. Note that I tell you this is relative, right? So let's say, for example, I fix this local index. Okay, I call it R1, R2. Okay, remember this local index? So let me recall again. So I got two line. I recall again. You got two curves. Find the intersection. You have this L. Take the arc, clockwise arc, from the first one to the second one, and then go through this pi, draw this. Okay, and then we will get some number out of it. Okay, so my R1, R2 is actually this number, this kind number here. Okay. 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 So let's say we fix this two. From what we discussed just now, we should able to get this intersection here from this number. Okay, let me make it bigger. Now, so the question now is I want to know, want to compute the local index here. To compute the local index. So is the mu from C from D2 to C with mu D1 to C is R1, R2. Okay, this is the question. So how I'm going to use this homology or everything, lifting stuff. Okay, so first of all, we know how to lift the purple D with the orange B. So let's draw it. So I draw it as this. Okay. And then I also know how to lift oh, okay, sorry. So this so note that this this how to say this the arrangement, the arrangement is very important. So C and D2. Okay, let's write down. Okay, let me write down the formula. So there's a remark here, not remark, but important proposition. So this is equal to 1 minus 0 minus, if you swap C0 and C1, if Z in delta, not in delta, and 0, 1, if maybe I just go through this proposition so that it's clear in the definition. It's clear how to do the computation. So for this computation, you just go back to my picture again. So this is 0, this is 1. Okay, you draw a circle. So mu C0 C1, where do you get it? You can get it here from this path. Give you mu C0 C1. But now in this case, you want to compute mu C1 C0. So mu C1 C0, what path you can pick? You can pick this one. Okay, this path will give you mu C0 C1 C0, right? Because this is a clockwise, so I'm picking the right one. So C1 to C0. But what's the difference between these two? So if I add up, if I go from C0 to C1, C1 to C0, actually I'm going around 1 RP1, right? Do you see it? So you're going like this. So these two paths act together is 1 RP1. That's why you got this formula mu C1 C0 plus mu C0 C1 is equal to 1 RP1. But I define RP1 to be what? To be 1, 0. Right? Let me go back to the here. Okay. And then similarly for the other case, I can quickly show you. So first you have C0, sorry, C0 to C1. But now you want to compute C1 to C0. What are you doing? You are going around a puncture. If you add these two paths together, you are going around a puncture. So going around a puncture is what? Minus 2 and 1. If you go back and check my definition. But not that. How many RP1 you go through? 1 RP1. 2 RP1. You got 2 RP1. So minus 2, 1 plus 2 is what? Is 0, 1. Let me write it down. So plus 1, 0, but this one times 2. Plus 2 times. So you get 0, 1. So that's why there's a 0, 1 here. Okay? So if you swap, they have this kind of property. It's not symmetry, but you have this proposition here. Okay. Any question? This also sheds some light how you compute these mu stuff. So, okay. Go back to my example just now. So, what you can do is this, and then this. Okay, why I know this? Actually, I missed up something. So actually, I need to tell you how I pick this BK and DK because different orientation or different arrangement will give you different number, right? So actually, I need to tell you that which clockwise arc I pick. Okay, so actually I'm picking right. So I've been picking I'm picking BK with BK plus 1. Okay, that's why I draw this arc here. And then I'm picking, this is not new. This is the phi greater. And then I'm also picking for DK with BK. So that's why I know this arc, this arc, this arc. Okay. So the question is, I want to compute mu D2C. So where is this arc? So it's going from D2 to C. So it's here. Okay. Of course, you also can pick this the top guy here, but this is more convenient. Okay. And then what else? Did I miss out anything else? Okay. So okay. So you can actually somehow see that this, if you're going through this thing, you will form a loop in this topology here. So let's move it and then draw it. Okay, I think we are out of time. Maybe I will stop with this example and then continue with the graded Floer Cohomology next time. And then I also need someone to help me to read the differential geometry part. I will say later. But let me finish this example first before we end. I also have to leave at 12. So okay. So let's do it. So do this example. So okay. So we need to get a loop out of this. So how should we do it? So if you cut the picture out, so let's cut the picture out. So what we get is C, okay, C, and then we got this part here, we got this part here, C, okay, we can look at this, we can look at this, we also can look at this actually, right? Because I already tell you how to swap from the bottom clockwise to the other clockwise. So let's write down. So this is mu what? Mu b. Let's call it b1, b2. So b2 with d2. Okay. Just now we already know mu d2 and b2, but this is just swapping. And then we also can take this one. Okay. But what we want to compute is this. Right? Okay. No question. Not that actually you can actually isotope your C to a straight line, right? So that it doesn't cause much problem in our RP1 computation, we just, for convenience, we can isotope to straight line. Okay. Isotope to straight line. So where's the eraser? So that it doesn't cause much problem with isotope to straight line. Okay, we have a diagram here now. Okay. So let's try to add up all these circles. What do we get? So we get mu d2 mu so what we get? So we start from maybe, okay, we start from this one, the red one. Red is what? Red is the one we want to compute. Is d2 with c. And then going across c, we don't move RP1. Okay, so let me draw it out. So we move RP1 to half of it, and then we stop, and then we go to C, and then we move, and then go down, and then we move, and then move, and then move. Okay? So what we are adding is mu d1, d2, C, and mu C with d1, and then plus mu d1, b1, plus mu b1, b2. Correct? Yeah, correct. Mu b2 d1. Okay, all correct. If they are clockwise oriented. So you need to compute how many RP1 you go through, how many puncture you go through. So in this case, we actually avoid the puncture. So there's no punctured homology coming in. So, but we already moved RP1, right? So how many RP1 we have moved? So we're going down, 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 up. And then actually going from here, going down, right? It's actually the same as going up, correct? If you're going, okay, going through here is going like this. But if you reflect it up, because this is RP1, so this is equivalent to going up. Agree? Agree, okay. And then going down again. So going down, 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 down again. It's actually you're going the same way, okay? And then similarly, you can all compute it. Actually, you go through 3 times RP1. Okay, so you get 3 0 here. 1 0 times 3. 1 0 times 3 times 3. Okay, so you get 3 0. Can you see the 3? Okay, so the next thing is to figure out to write these things out. Okay, this is unknown, these are given.
Okay, can you also draw the pi vector on C or on the orange line?
Pi vector on C is just straight. It's just straight. Okay, let me, how to draw? It's like this, like, yeah. It's like this. On C is the normal one. On this alpha thing is an unusual one. You take like not equal to the tangent. Yeah. On C is the normal one. So that's why I isotope to the straight line, so that you don't need to care you go out or go down. Actually, they will cancel. Yeah. Yeah. So there's an isotopic invariant here. Quite interesting. Okay. Okay. So so let's try it all out. So I swap to the things that I know. Do I know CD1? Okay, I don't know. What I know is I know D1C. Okay, so I swap it. And then do I know D1B1? I know. And I set it to 0, 0. Okay, this is how I pick my grading.
Other Nakajima clover varieties.
And then B1, B2 I know. Okay, because this is how I pick my leaf. This one. Okay, I pick them to be 0. So both of them 0, 0, 0, 0, and then plus B2, D2, do I know? I don't know. What I know is D2 and B2. Okay, so if you move them around, you will get BD2C is equal to okay, this one I know, right? This one I know, but this is 0. Okay, this is how I pick my bigraded. Not that I don't put tilde here. You can put tilde yourself. So this mu is always referring to the lifted one. So what I get is 3, 0, minus 1, 0, minus 1, 0, plus mu D1C. And then this is what? This is 1, 0, plus R1, R2. So that means if you give me R1, R2 here, I go up. And then this is fixed to be R1 plus 1, R2. So you know part of the curve, everything you know. Okay. So okay. So this kind of calculation, of course, you can extend it to something like this. Computing this local section here, the bigraded intersection number. You can extend to this example. But I explained this example so that you can understand the paper when you read it. Okay. If got time or required, maybe we will explain what's the relation between the Poincare polynomial with this intersection number, going from topology to algebra. But the next thing we need to do is to understand the graded Floer cohomology first. But I don't think I have the time to do the setup. But I hope next time, either Brian or any student of here, because this is, I think it's differential geometry stuff, can help to explain example 5.16 and also lemma 6.17, because these two, because to understand the grading, you need to go to the explicit trivialization, which is above example 5.16, using those pullback and explicit pullback, and yeah. But next time I will compare this two construction. I mean, to get the covering in the topology and also the covering graded covering in Lagrangian submanifold. So I wonder if Brian or any student of here can take out the differential geometry part. I really want to see the calculation.
Can you put the page to the reference?
Yeah, sure. I can. It's page 57.
I mean the name of the reference. I didn't.
Oh, name of the reference. Name of the reference.
Could you just bring it up on your tablet?
Oh yeah, this one.
Bring out my tablet.
And
yeah,
in fact,
so we can
this
all just.
Okay.
theory, I guess, was more recently studied by Kiventhal and one of his students. They call this quantum Hertzebruch K-theory. There is very interesting stuff to study about functions like this. But the problem for us is while these things are balanced, while this twist of the J function is some balanced thing, it doesn't seem to satisfy any nice Q difference equations.
Hey, Brian.
Or at least not that I
Yes.
Your mic's unmuted. We can hear your lecture.
Additional twists that you have to do.
Thank you.
Okay, I just point out what I want to know from you all. I want to know. Actually, I want someone to explain this. They are quite explicit. I just that I'm not familiar with those things. 4, 5, 6, 7. Okay, I want people to explain this. Can I point? I can't point. Okay, I make it to good note, then I can point. Okay, I go to 57. I think someone here can explain. So I want someone to explain this part. Okay, explain what is this, explain what is this, explain what is this. And then this, and then do this example, and then compute this. Compute. If you can't compute this, never mind. But if you can, then you can do. But this one. Okay, why is this important? Is because if I go to lemma 1.4, 1. Yeah, there's a lot of like this kind of construction here. You also can explain, I think, using those kind of argument. And then yeah, this one. So the important is explain this lemma 6.17 because I really want to know how to get this. I want to generalize this to type B. So I need to know how they do this calculation. So the part I don't know is this. What this thing is. And also this, why is this a bigraded Lagrangian? This one.
Well, how about Keating on Thursday or Friday? You can't come in here, we can go through it.
Sure, if you want.
Yeah.
Yeah. But hopefully someone, yeah.
Okay, so I let you to figure it out before like Monday. We have a meeting on Monday. If still some difficulty, then maybe I jump in on Tuesday next week and spend a few hours. I just have so many things at the moment. Maybe I will leave you to figure it out.
Yeah, maybe Matilda also